So far, in the previous 2 days, we covered the basics of quantum information processing, what are quantum states, what are quantum dynamics. Yesterday, we looked at one particular quantum algorithm as well. So today, we're really going to shift gears a little bit. We've also seen quantum state tomography. We now know that it's easier to measure photons, and we can also generate entangled states with the process of spontaneous parametric down conversion. So some things are easier with photons. It's easy to generate entangled states, and it's quite straightforward to measure quantum states using elements such as quarter wave plate and half wave plates followed by polarizing beam splitters and just measuring the counts of photons. So initialization is easy, readout is easy, 1-qubit gates are easy, but we still do not have a universal quantum information processor because we need 2-qubit gates as well. So, and the good thing about photons is that they do not decohere, they do not interact very easily with each other or with the environment. That's why you can send them off over long distances with little loss or minimal loss as compared to other techniques. The photons really qualify as flying qubits. They can be transmitted from one location to another. You cannot do that with atom waves or matter waves or cold ions or neutral atoms, etc., or spins or squids. Photons qualify as the transmitters between two distant locations. So that's good about photons. The problem with photons is since they do not interact with one another, you cannot easily make 2-qubit gates. So can we use the measurement capability of photons to make 2-qubit gates? Well, it seems very counterintuitive because measurement, especially projective measurement, is an irreversible process. So if I have a quantum state and I measure it, the original state is gone in most cases, unless you measure an eigenstate of the measurement operator. The original state is gone. It's a destructive process. It's a demolitive process. It demolishes quantum state in most cases. So it's an irreversible process, but gates are unitary processes. They are reversible. So how can you achieve a reversible process through an irreversible process? So it looks very difficult to do so and counterintuitive, and there are two contradictory tasks that you would like to achieve. However, measurement can be used for doing gates and information processing. So this is the idea that I would like to discuss today, and especially closely related and very amenable to photons. Photons are a good candidate to demonstrate measurement-based quantum computing schemes. And Professor Orton really mentioned that he wanted me to emphasize on measurement-based computation. So today I would like to focus on this topic, and especially the different means of doing measurement-based quantum computing. The one method that I will describe today, and I will describe it at a fundamental level so that it becomes easier for you to understand. And you can do calculations on your own. And that is the ideal cluster quantum computing, cluster states. So let's start our expedition for today, and let's focus on measurement-based quantum computing, okay, for MBQC. With a special emphasis on cluster states. So it all started off with the idea of where did this idea of measurement-based quantum computing come from? It came from the idea of quantum teleportation, in fact. So I hope you all know about quantum teleportation, right? What do you want me? I can give a brief overview. So in quantum teleportation, in the simplest form, you all know that we have a circuit. And the circuit is such that suppose we would like to teleport a quantum state psi. So you want to teleport this qubit. This is one qubit teleportation. So with psi, you also create an entangled pair of photons, say in state 5 plus, the Bell state. This is an EPR pair generated, say, for example, by non-convergent. Easy to generate this in the laboratory, and the top line is another qubit that you like to teleport. So one of the photons in the entangled pair goes to Alice, and the other goes to Bob. So this goes far away. This goes to Bob. This is Bob's world, and here we have Alice, and Alice does a quantum state measurement, a Bell state measurement, so which is really a controlled NOT gate followed by a harmonic gate. Okay, on her qubit, which is in an arbitrary quantum state A cat 0 plus B cat 1. So she does a measurement. So she then has these detectors. So a beam splitter, polarizing beam splitter here, a polarizing beam splitter here, two output channels cat 0, cat 1, cat 0, cat 1, and she gets four possibilities. The four possibilities that she gets are so she should either get 0, 0, 0, 1, 1, 0, 1, 1 for her two qubits, correct? Now this is she does the Bell state measurement. She measures the state of our photons in the horizontal vertical basis, for example, in the computational basis, and she gets these two bits, these two classical bits as an answer, either one of them, with equal probability, with 25% probability each, and then she communicates whatever information she gets on a classical channel to Bob over classical channel, a phone line, fax line, email, something, piece of paper, or a pigeon, or anything. And then Bob does, based upon the information that he receives, he does a polygate for some unitary operator on his qubit, which was originally one photon in the entangled pair. And this U could be a polygate, like an X gate, or a Y gate, or a Z gate. And lo and behold, finally, the qubit. Bob has not yet made any measurement on his qubit, so finally Bob's qubit will be an exact replica of the original qubit that Alice wished to teleport. So this is the quantum teleportation scheme, and I hope you can go through the calculations step by step in a methodical fashion and see that this is true. And you can figure out the formula for the application of any of the polygates. By the way, one of the polygates is also one of the gates is also identity to nothing. So if Alice gets 0, 0, Bob's qubit is an automatic copy of Alice's qubit. So this is, you're all familiar with this quantum teleportation scheme. Now here a qubit is being transmitted. It is being teleported. So now measurement-based quantum computation. So this already has some inkling of measurement-based communication or measurement is kind of important here because one party is doing a measurement and that measurement is a classical result is being transmitted to another party and the classical information is being used. The measurement is being used to do something useful. So measurement is playing an important role here. Likewise, the same idea can be translated into doing computing with measurements, which is measurement-based quantum computation. So now let's shift gears a little bit towards yes, please.
First of all, both has exact same start state right now, right?
Yes, or you can convert it into the exact same state.
Okay. So in this case, what happens to no cloning theory? Isn't it cloning?
No, but the original qubit is destroyed. Cloning means you have one copy of the original state and the original state as well. The original qubit is destroyed. So the first qubit, Alice's qubit, shown in white here, is demolished. It's gone.
Second question is, Bob has exact same precise state, but he has no knowledge about alpha and beta, right?
How?
He has no knowledge about alpha and beta values, right?
Right.
I mean the vertical and horizontal
Right.
coefficient.
Yes.
In this case, if he wants to get the information or use the information of alpha and beta, he can only do quantum tomography, I guess, right?
He can do any measurement technique. Yeah, he would, if he wishes to find out the state, he will do that, but he will destroy the state in the process.
Okay, what I'm trying to reach is the information about alpha and beta.
Mhm.
I'm just trying to find out what the value for.
Just decrease the volume a little bit, perhaps. Okay, please go ahead.
Okay, my question is, how can I get the information of alpha and beta? There's only one way I guess. It's only a quantum state tomography.
You can do full tomography or you can do partial tomography, yeah, but it's called tomography.
Okay, thank you. Anyway, okay, thank you.
No, please go ahead.
I'm just wondering about half and full tomography.
How?
What are those? I have never heard the full or half tomography. I only heard state tomography, and I don't know about half and full.
So now if you have some prior knowledge that this is a pure quantum state, or it is a linearly polarized state, or it is a computational state, then you don't need to find out and all of the components. So it means if you have some prior knowledge about the state, that the state is probably in this subspace, then you don't need to do all the measurements. That's what I'm saying. But you need to measure alpha and beta separately. And the no cloning theorem is related to the theorem that you cannot measure a quantum state in one go. It's the same thing. No cloning really means that you cannot discriminate non-orthogonal states.
Okay, thank you so much. So I have one more question.
Yes.
Is this like only one copy or a bunch of copies?
So I should understand the question. So these are just three qubits, three photons.
Yeah, I get that. Right now, Bob has precise state, right? It's
Yes.
not like just one particle, I guess. It's not like that, right?
It is one particle. It could be one particle. There's one photon, or may have one photon. So Alice is fed in with two photons. Alice gets one photon which she wants to teleport. That's one photon. And we have a pair of photons here. Two photons go to Alice. One photon goes to Bob. It's one photon. You just have one photon, and that's it. And that photon goes to Bob, and Bob's photon will be a teleported version of Alice's photon. One photon.
So once he measure it, he will only get one or zero, that's all.
Right. So he cannot measure it in one go. But that's a different point. Measurement requires many copies. If you want to build the statistics, you cannot measure alpha and beta without building any statistics. Statistics requires multiple experiments on identical experiments.
Thank you so much for your time.
Yeah, but we get.
I'm just trying to encode some information and decode it. It's one of the problems I'm facing right now, so that's why I asked you. Thank you so much for your answer.
Okay. All right. So now let's come to the idea of one bit teleportation. Now, one bit teleportation is a means of using measurement to encode or implement quantum gates. So let's see how that is done. So this idea was proposed by Gottesman and Schwank after taking inspiration from the idea of teleportation. So before I'm able to describe one big teleportation, which is like a teleportation trick, I just want to mention that if I have a unity operator, which is on a single qubit, so I make a rotation to theta about an axis on the log scale. I can always express this rotation in terms of three rotations about two orthogonal axes. So I can express this as a rotation about z-axis to alpha, x-axis to beta, and z-axis to gamma. So where I define, so let's look at how I define things. So I'm using this rotation a little bit. X, y, and z, my polyoperators. Okay, without any argument. But if I write x, say beta, with an argument, it means exponent minus I beta x by 2. Alright, so it's a rotation about the x-axis of the block sphere to an angle beta. So this is my notation. Right. So x, when I write x without the argument, it's really the Pauli operator, just the Pauli operator, which is equal to x with beta equals pi. This is exponent minus I pi over 2x. Okay. So x, y, and z are the Pauli operators, and x, y, and z, the arguments are rotations about the x, y, and z axis to certain angles. Okay, so this is the notation that I'm going to use. Now, any rotation, single qubit rotation, we try to reduce the noise. So any single qubit rotation can be written as a concatenation of three rotations, one about the z-axis, then about the x-axis, then about the z-axis. And when I write this in operator form, my time flows from right to left. Time goes from right to left. But this atom quantum state is from the right. So this is the ordering operation or ordering that I'm going to follow in writing the operators. Okay. Now, if I were to make a diagram for this, however, so the diagram for this would look like this: Z alpha followed by X beta followed by Z gamma. Okay. So in a diagram, in a circuit diagram, time flows from left to right. Okay, so this is general convention that you find in papers and research articles. Okay. Now, the arbitrary rotation can be written as three rotations to z x followed by z, or you can have a y in between as well. Alpha, beta, and gamma, if you study classical mechanics, they're called the Euler angles. They're Euler angles. So any rotation in three dimensions can be represented by these Euler angles, alpha, beta, and gamma. You can have an object rotated through three kinds of angles in succession. You will get arbitrary rotations. Okay, you must have studied this in classical mechanics. Anyway, this is the scheme that we're going to follow, and probably as a homework, you might like to verify that these. If I would like to achieve a rotation of theta, then my theta must be equal to alpha plus gamma, and my sine beta over 2 equals sine of theta over 2 sine of beta over 2, excuse me, sine of beta over 2 equals sine of theta over 2 into sine of alpha. Okay, so you can prove this. This is a homework problem. If you want to have this equation to be true, theta and the axis of rotation must be related. Alpha, beta, and gamma cannot be arbitrary. They have to be chosen in a particular fashion so that you achieve your desired rotation. Anyway, you can prove this as homework. So any rotation, any single qubit rotation can be decomposed as z followed by x followed by z. This is key in understanding what we're trying to do. All right, so let's move on.
And how to relate the n with the alpha beta dominant here?
Okay, so this.
Because you see that in the rotation around n theta. So there is relation.
Just, I've done this calculation. Just a minute. Let me show you how. Okay, so the answer to your question is the following. So R n theta. Now what is n? N is the axis of rotation. This is, let's call this amount of rotation. Let's, instead of writing theta, let's write it as A. Amount of rotation, A. Now n is sine of theta, cosine of phi along the x-axis plus sine of theta, sine of phi along the y-axis plus cosine of theta along the z-axis. This is my axis of rotation. Now with this definition, I have the following. And the definition is that my angle beta, sine of beta by 2 equals sine of a by 2, which is the amount of rotation, into sine of theta. Okay. And my alpha plus gamma equals 5. Okay, so this is our calculation. So now I have the axis of rotation, phi and theta, included in how I calculate my alpha, beta, and gamma. Okay. So now everything is all right. Now let's move on to the idea of one-bit teleportation. Now in one-bit teleportation, suppose I have two qubits. One qubit is in the state psi. The second qubit is in state at 0. So, and now what I do best state, the same circuit as I have for teleportation, control not gate followed by header 1. Okay, so this is similar to the teleportation circuit, but you're missing the EPR pair, you're missing the timer photon. Now let's see how this circuit evolves. First of all, my psi could be A0 plus B1. So my initial state is A00 plus B10. I apply the control NOT gate, G NOT gate, and I get A00 plus B11. Then I apply header NOT gate on the first qubit. Okay, I get A 2, 0 plus 1, 0 plus B open to 2, 0 minus 1, constant 1, then expand this out 1 open to 2, A 0 0 plus A 1 0 plus B 0 1 minus B 1 1. Okay. Now what I could do, I could write this as A. Sorry, I could write this as get 0 cross with 1 over root 2 A plus A 0 plus B 1 plus get 1 cross with 1 over under root 2 A 0 minus B 1. Okay, let me read all the circuit, control NOT gate, Anwar, side, X0. So now what I could do, I could do a measurement on the first unit. Right, I do measurement. For example, I can put a polarizing resistor. So we're talking about photon, we can put a polarizing resistor and look at the work channels. The outcome will be 0 or 1 on the first unit. So the outcome K can be 0 or 1. These are two possible outputs. Now, if the output is 0, the second qubit will collapse into this state, which is the original quantum state. And if the output is one, k equals 1, then I re-implemented a z gate on the first qubit. Right? So the second qubit is reading the state is in z raised to power k on the first qubit. Now what this has achieved is you have implemented a z gate on the second qubit, provided you have knowledge of the measurement outcome on the first qubit. Correct? So this measurement outcome K is fed. This information is provided to the observer here, is available here. So you have a measurement outcome, there's a readout here, you get some measurement outcome, that measurement outcome determines what the other qubit is. And the other qubit is in a state which is a transformation of the original. So a gate has been applied to the original qubit. Okay. And that gate depends upon the measurement outcome. If k equals 0, then the gate that has been applied is identity. And if k equals 1, then a z gate has been applied to the original qubit. So this measurement has now really imposed a gate on the second qubit. Now what I could do is I could now kind of let's try to modify the circuit a little bit. You do know how to implement a control NOT gate. A control NOT gate is really a control phase gate followed by two Hadamard here and Hadamard here. I think I mentioned this on the first class. So now let's try to modify this circuit in sequential steps. So what I would do is, instead of NOT gate, I put a control phase gate and a Hadamard gate here and Hadamard gate here. Just the same. Hadamard measurement outcome is K. So this is the same as the original ZK. Correct? Now what I could do, this really means that I could do another successive change. I could replace this second qubit, the Hadamard gate acting on the first qubit is creating equal superposition of ket 0 and 1. So that means it will talk about polarization. So let's call this plus. Ket plus. Ket plus is ket 0 plus ket 1. Okay. So this becomes this. Hadamard Okay. And I can just, I have created HZK. Or I could just what I've done is I've just kind of taken this H gate further ahead. Now what I could do is suppose I now apply HZK. We have to apply this gate, okay. Now there is a kind of there is, let's look at this gate HZK. So I've taken this Hadamard gate and just moved it forward. Now what I do have is an identity that HZ is equal to XH. This is an identity. So if I have a Z gate followed by a Hadamard gate, it's equal to having the Hadamard gate followed by the next gate. Okay. You will do this simple calculation. So what I could now do is I could replace this HZK with an XKH. So I can replace this cycle becomes the following: control phase, Hadamard gate, measurement, and this HZK I can write as XKH. Sorry. Okay, so I've just made this replacement HZ is replaced with XH. To improve this, when I have mathematics in the second half of my lecture, just remind me I can show you a simple calculation of how this is done. Z gate followed by an H gate is equal to an H gate followed by an X gate. Okay. Now what I could do as the next step is I have this circuit in front of me, psi input and a cat plus input, controlled phase gate, Hadamard gate on the first qubit, followed by measurement is equivalent to having this unitary operation act on the original state. So through a measurement, I have applied a gate on the second qubit. Now what I could do in the next step is I could suppose my original state were I apply a Z alpha gate to psi. Okay. So to psi I apply Z alpha gate. What's going to happen now? H measurement K X. So what have I proved? X K H instead of psi. Now I have Z alpha psi. Right. So this is just a sequence of operations. I mean I kind of made it really simple for you to understand the entire paradigm of measurement based computing. At least I've tried to do so. So now what I've done in the initial quantum state, I've applied a Z operation. So I rotated to alpha about the Z axis. And then this state here becomes psi, Z acting upon psi, Z acting on psi. That's what I've done. Very simple. So far, so good. Now the point is that this is a controlled phase gate. Can I move this Z gate across the controlled phase gate? Can I do that? How will I be able to tell whether I can move gates around? Sorry? Right, so I need to know the commutator of this gate with the control of this gate. If that commutator is 0, I can move the gates around. The order does not matter. So if you look at the matrix version of this control phase gate, it's a diagonal gate. Yeah, you know it's like 1, 1, 1, minus 1. It's a diagonal gate. So diagonal gate commutes to actually everything. So I can take this block and move it over here. Doesn't matter. Okay, so let's do that. So psi 1 control phase gate here, Z alpha, H, I do measurement, outcome K, X, K, H, Z alpha, psi. Okay. Now if I would like to put both of these gates in a box, in one box, first Z is being applied followed by H. So this is the time order. So if I put both of these together as one operator, I can just, for convenience, write this as psi for phase plus Z alpha followed by an application of H measurement K and say qubit is seeing a transformation X K H Z alpha. Okay, so this is my final circuit that I wanted to emphasize. What this circuit really is that this circuit really is two qubits coming in. The first qubit is in an arbitrary state, and we wish to apply a gate to it, even though it's a single qubit gate so far. So what you do is you prepare an ancillary qubit. So now you want to apply a gate to one logical qubit, but you have two physical qubits, and then you do a controlled phase operation between them, and then you do a Z rotation on the first qubit, followed by a Hadamard gate and measure the first qubit. So doing an operation on the first qubit, followed by Hadamard, and then a measurement is really, you're doing a measurement in a basis, in some basis. You're doing a measurement in a particular basis defined by the choice of alpha. Okay? You're doing a measurement in a basis defined by the choice of alpha. So you're really making a measurement in a basis. The top row is a measurement in a basis. Let's call that basis B alpha. It's defined by the choice of alpha. So what really this basis is, if I look at the block sphere, alpha is determining which orientation are you measuring along in the equatorial plane of the box sphere. So this orientation is defined by alpha. So you are rotating the state by alpha, which means you're measuring in a basis which is now a rotated basis. It's the equatorial plane. So the first stage is prepare your physical qubits in a particular state, do a controlled phase operation, and measure the first qubit in a basis. You choose the basis because you choose the alpha. Now there are two possible outcomes. A. So it's a single bit here. So there's two possible outcomes, 0 and 1. That outcome determines what you have really applied, what gate have you applied to your original qubit. So this is classical information. That classical information is available to you, and it determines what gate have you applied. If you want a particular gate, you can unwind it by applying the reverse of this. So measurement-based quantum computation is also very kind of inclined and amenable and related to the idea of quantum error correction as well. So it's the same idea. So this is how you have applied a gate to the first qubit. But really you don't you really want to apply a sequence of gates. Because your arbitrary rotation, which I have over here, is a sequence of gates, Z followed by X followed by Z. So you just don't want to apply a Z gate, you want to apply an X gate, and you want to do it in succession. You want to apply these three gates in succession. So you want to do a higher dimensional version of this one big teleportation circuit that you just did. So I'm going to do that right now. So the basic idea is you measure in a particular basis, you measure one qubit in a particular basis that is equivalent to, or tantamount to applying gate on the second qubit. Through a non-unitary process of measurement, you apply the unitary operation. That's why this is remarkable. I mean, if you look at this from a philosophical angle, this is remarkable. Doing something irreversible is giving you a reversible operation. Now let's kind of take this idea a bit further and see how we can implement a full arbitrary one qubit rotation to this measurement process. Okay, so now what we could do is we can build another circuit, so that we call that circuit. So now I want to do three operations, Z followed by X followed by Z for an arbitrary rotation. So I will need more physical qubits. Even though my logical qubit is still one, I need more physical qubits, I need more resources. And I'll show you how these resources are readily available with photons. Now, if I were to kind of expand the circuit that I've just drawn, it will look like the following. I have now, the state on which I wish to apply an arbitrary one qubit rotation through measurement. And I have three additional qubits, each one of them initialized in a superposition state. And then I apply control phase here, control phase between these games, control phase between these games. And similar to what I've done, I apply H, Z alpha here, and measure. Let's say the outcome is A. Apply H, Z beta to the second qubit, and measure. Let's say the outcome is L. I apply H, Z gamma here, and measure. Say the outcome is M. And then all of this information is made available. This information. All of this information is made available at the final qubit. And at the final qubit, this final qubit finally will have H, Z alpha, X, K acting on side. Similar to what we had over here. X, K, H, Z alpha. Followed by Z beta, H, X, L, followed by Z gamma H X M. So my time in this operator goes like this. So what I achieved is by that 4 physical qubits, I applied logical operation on one encoded qubit. And that logical operation is ZH followed by X. The X, whether you apply an X or not, depends upon the measurement outcome. Followed by rotation of V, H, and X. Whether you apply an X, this X exists or not depends upon the measurement outcome, and so on. So this is similar to the original 3 qubits Z that we were. It's similar, but it has a string at least constructed, and we can refine it further. But now what we've done is we've applied these 3 measurements to 3 qubits in particular bases, alpha, beta, and gamma. And we choose those measurement bases. And the outcomes, the bits that come as an outcome, now there are 3 bits, that determine what kind of gate has been produced. Okay, so the gate that has been applied here to our qubit is Z alpha, H, X, K, Z beta, H, X, L, Z gamma, H, X, M. Now, what we would like to do now is kind of simplify this expression a little bit. And we can use some tricks to do that. The first trick I've already mentioned is that HZ is equal to X H. This is one trick. One formula you would like to say. The other formula is that if I have Z to some beta X, this equals X Z minus beta. This is another formula. Okay, so these are just identities, the poly operator and the diagram. These are just identities, you can prove them by direct calculation. And if I have X to some power P, and then you have minus 1 raised to power P. Okay, so you have identities of this kind.
The operators with the arguments, right? They are the exponential unitaries. They're not the bodies themselves.
They're not the polys themselves. But they can be expressed as a combination of polys, not the polys themselves, and without the argument is a rotation to pi, which is a poly itself. If you don't have the argument, it's just a simple poly operator. And a simple poly operator is exponent minus iota pi and the poly operator. So it's with some global phase. So with these identities, you can kind of manipulate all of these expressions. And when you manipulate all of these expressions, you can take, you can take all the x's to one side, take all the x's to one side, and you're left with an expression that you can probably do as homework of this kind. Psi out is xm zl x k h z minus 1 l gamma h z minus 1 k beta h z alpha. So this is really hz alpha followed by, suppose my K and M are just one. Let's suppose it is one, measurement outcome is one, because the algorithm proceeds if the measurement outcomes are zero. Otherwise, you have to adapt the algorithm and adjust the angles every step. So let's assume that the outcomes are zero. So you have HZ alpha followed by HZ beta followed by HZ gamma followed by this factor, which is some factor, right? Which is a combination of all operators. So now you have a string of operation on the qubit. HZ alpha followed by HZ beta followed by HZ gamma followed by U. Okay. Now this, by the way, HZH is an X operator. HZH, this HZH is an X operator. And that you can see. So you see here, HZ, you post multiply with H, get X, HH. HH is an identity. So a Z sandwiched between two Hadamard operators is really an X operator. So this thing over here, HZH, this thing, if I switch these, which I can easily do, then I can get an X operator. So I have a Z operator followed by an X operator followed by another Z operator. This is an arbitrary rotation. Sorry. This is an arbitrary rotation. I will apply an arbitrary one qubit rotation through measurement alone. Now the question is how to apply two qubit operations to measurement alone. Alright. So it's easy to measure photons. So you prepare the photon in a particular state. You have a certain input state, which is called a cluster state. You do a measurement on some physical qubits, and the other qubits see a transformation. Or the logical qubit sees a transformation. This is applying gates to measurement. Now we will put everything together so that we can do some useful things out of this. So by the way, this original circuit that I have over here, I can kind of redraw this circuit in a more intuitive fashion to show you the yes, please.
To apply the measurement, you need to have all of the output to be zero. I mean, you have to get this to apply this gates.
These gates.
Yeah, the first three measurements should be zero, right? The output. I mean,
right. So if the measurement outcome is zeros, everything works error free.
But if you use qubits, then the probability that having all of them to zero
is low. Is low. If you don't have zeros, still you have an expression. So if this is say 1, you still know what gate has been applied. So you can, it's adaptive. So it proceeds without any forward feedback if the outcomes are 0. If any one of the outcomes is 1, then you need to have some feedback. That is error correction. That can be easily done because you know what the outcome is and you know what kind of correction needs to be applied. So it proceeds error free without feedback if the measurement outcome is 0. Otherwise, you need to do error correction at each stage. So now let's look at this circuit. Now I'm going to redraw I'm going to redraw this circuit in a more intuitive fashion so that the process of measurement based quantum computation comes together. Remember that this is only acting on second qubit, third qubit, first qubit. So it doesn't matter in what order this is applied with respect to this. So what I could do, and all of these commute with one another because they are phase gates. All can go in either direction. So what I could do, I could just redraw this circuit for understanding purposes in the following fashion. So I have so this step followed by this step followed by this step. Okay, so I can have three successive steps. First, I just measure on the first qubit, get transform. Then I use that information for feed forward. I then can measure on the second qubit, then on the third qubit, one after the other. If I have more qubits, I can use each measurement outcome to affect what I do to the other qubit as well. But I'm not doing it here, but it can be done. So how this entire idea progresses is in the following fashion. First of all, I so now I'm gradually moving to the idea of cluster state computing. Okay, which is one kind of measurement based computing. So I have my physical qubits, the photons in my case. I need to prepare an initial state. Suppose I represent my photons in this diagram here. These are my 4 photons. And I'm talking about, say, any degree of freedom, like a past degree of freedom. I really prepare each of these photons. First state is prepared. I prepare each of these photons in the state F plus. 0 and 1 are my computational states, and I prepare them as each one of them in this superposition state. Then I wish to make bonds between them. So preparation means the first step of preparation is to prepare them in the superposition, and then for bonds, I apply control phase operation between any 2 photons that have a bond between them. Okay, that's what we do. So I have these 4 physical photons, physical qubits, and I prepare each one of them in the state F plus, and then to control phase operation between, say, if I label my qubits in the following fashions. So 1, 2, 3. 1, 2, 3, 4. I do control phase operation between 1 and 2, a control phase operation between 2 and 3, control phase operation between 3 and 4, and control phase operation between 4 and 1. So now this is my initial state for cluster-based computing. This is called a cluster. I have now prepared the state. Somehow. And I show that with photons it's easy to prepare such states. I'll give you an example. Now I prepared this state. Now these states are laid down on a topology, on a diagram. What I do is I have 4 physical qubits. and two logical qubits, suppose. What I do is time proceeds from left to right. What I do is I make a measurement on qubit 1 and qubit 4 on a particular basis. Some measurement. So cluster state probability starts off by preparing the state. The cluster is given to you. Okay, the state, which is now called a cluster, is given. It's a resource that is prepared offline. Okay, it's easier to prepare such a resource by photon. So it's prepared offline. Offline means it's given to you, it's before the computation. And then, when you have drawn the diagram, you choose from left to right these photons that are connected in a single column. They are measured. Each one of them is measured. And you choose the measurement basis for photon 1 and for photon 4. So suppose the measurement basis is defined by angles alpha and beta. Okay. So the measurement of photon 1 takes place is defined by alpha. So the original this operation that you apply, which means you rotate the qubit along alpha above the z-axis followed by gamma, followed by measurement is really measurement in a particular basis. So you measure the photon in a particular basis. It's easy to implement measure in a particular basis by quarter wave rates and half wave rates, and then do measurement. It's easy to do. So you measure in the first stage of the algorithm, you measure photon 1 and photon 4 in their respective bases. Okay. So the second stage is measure in your desired basis. And you have to choose alpha and beta. Alpha and beta will determine what kind of gate, 2-qubit gate, 1-qubit gate that you're planning to use cluster state. So you have to choose alpha and beta. That's the only tough part. You have to choose alpha and beta. I'll show you examples of how you do that. So now you choose the alpha and beta and make a measurement. And for each measurement, there are two outputs, 0 and 1. That's it. So you get a 0 and 1 on the first, 0 and 1 on the second. Alright. So that now determines when you have made this measurement. In this particular case, when you have made this measurement, you just read out qubits 2 and 3. Okay. No further measurements are needed as far as computing is concerned. You do a final readout on these qubits. Okay, and your qubits, those qubits, in effect, will have tried a multi-qubit gate to qubits to your cluster qubits, your encoded qubits. I'll give you examples of this. So this is how the algorithm progresses. So you do a preparation, followed by a measurement, and then if need be, you have feed forward, followed by readout. I give you examples, don't worry. So suppose I have a cluster state of this kind. Suppose this is my cluster state. Okay, so now I have 8 physical qubits and probably 2 encoded qubits. I do a measurement on these 2 qubits in basis alpha, beta, followed. Now the outcome might determine what basis, what angles do I choose for the basis measurement on the second column of qubits. So I do some gamma delta basis measurement here. Then I do the outcome may determine what I choose for the basis measurement on these 2 qubits. So this is feed forward. finally, the end result will be available here. So you read out these two bits. And your end result will be available. This is measurement based on computation. Now, I'll give you plenty of examples for this. So just one idea which I think is important to example that I would like to give at this stage so that your confidence in this technique is established and substantiated. So example. So one example. Let's take a very simple example. I have two photons. Two photons connected by a controlled phase operation. This is my cluster, initial cluster. So it's not very useful, but it's a great example. Now, what is this? Is the cluster diagram or the topological diagram. Now, this corresponds to some physical qubits. Let's see what the physical state is for the two qubits. So, how do I prepare this cluster? Ket plus joined by controlled phase operation. So, let's see what I get. So, let's look at the physical description of this state in cat notation. So my first physical qubit answered with the second physical qubit is really. So I'm not kind of adding the normalization factor any longer because it's cumbersome. So this is really 0 plus 1 and 0 plus 1. Zero, 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 one, plus 1, 0, 1, 1. Okay. Now, if I look at this state, the next process is to apply a control phase between the two qubits. What the control phase between the two qubits does is that it just reminds things. Right? So this is the state that I had. This is the two physical qubits that are represented by the cluster state that I have drawn. Now let's go deeper into this state. So this state can be represented as this state can be plus one. Okay. This is what state has been paid. Now, if I were to do a local operation on the second qubit, is this entangled? Is this an entangled state? I think it can be converted to an entangled state by local operation. It's not separable. It's not a separable state. You can immediately look at this. You cannot write this as a tensor product of two sets. It's not separable. If you just had this term, it would be separable. Or just had the second term, it would be separable. So if I were to do a Hadamard, suppose I were to do a Hadamard gate on second qubit. So I do this operation. Nothing on the first qubit, and I Hadamard gate on the second qubit. So I just do a local operation. It's called a local operation. Then this state would transform into 0, 0 plus 1, 1, which is a Bell state. So this cluster state that I have drawn is equivalent to a Bell state, an entangled state up to a local transformation. So, and it's easy to produce Bell states. So if you have an entangled pair of photons, two photons, it is equal to this cluster state. You have already generated the cluster state. You don't need to do a control phase operation. With photons, the cluster state is easily available to us. This cluster state is easily available to us. And you can use this as a resource for measurement based quantum computing. So generating cluster states with photons is easy.
How could you actually implement a control phase between two qubits using photons?
Using photons, I will explain that with measurement based computing. I will explain that. I will give examples for that. So this is an example of how to prepare a cluster state. An entangled state qualifies as a cluster state. You prepare an entangled pair of photons with cluster state and this cluster state. Though it's not useful for cluster computing, but this is a great example. So let's look at one of these.
But to have an entangled state, you have to apply H after the application.
Yes, so
It's not just little.
right. So it has some entanglement. It has some entanglement. It's not a perfect bell state, but it has some entanglement. And it's useful for quantum computation, measurement-based quantum computation. You don't have to create a bell state, but it's the degree of entanglement in this is non-zero. It's not a bell state. No doubt about it. But it's equivalent to a bell state. Hadamard gates on single qubits are easy to apply. If you really wanted a bell state. So if you create an entangled pair and apply Hadamard gate on one qubit, which is just a beam splitter, say, then you have created the cluster state. Let's look at another example. Suppose I have three qubits. Three digital qubits and this cluster. Can you try to work out what the physical cat representation would look like? Yes. First stage is this, okay, which is just an equal superposition of all the three qubit states. I know you really want to see two qubit gates and phase gates and qubit, so I'm getting there. I'm getting it, inshallah. Just need to be methodical and systematic about it. So this is my initial first step of preparation is create each one of them in a superposition. And now let's say I control phase between qubit 1 and 2 and 2 and 3. Let's do that. So control phase between 1 and let's do it first, 1 and 2. 0, 0, 0 plus 0, 0, 1 plus 0, 1, 0 plus 0, 1 plus 1, 0, 1, 0, 1 minus 1, 1, 0, 1. That's between 1 and 2. And now let's apply between 2 and 3. And this is what it is. Now, is this rectangle or not? This is really, if I were to, you should do this as homework. I mean, it's very hard to do everything on the blackboard in the class. This is an entangled state. Now, can I show that? I can show that by, if I were to do a local operation and I get a maximally entangled state, then this should also be an entangled state. So if I were to do local operations on this state, which amounts to Hadamard gate on the first qubit, do nothing on the second qubit, and Hadamard gate on the third qubit. I will get the GHZ state, which is 0, 0, 0 plus 1, 1. Okay, so you need to work this out. So I do this operation, I will get this state, the GHZ state, which is entangled state for 3 qubits. Okay, so this cluster state that we have drawn over here, this really is an entangled state. It's equivalent to a GHZ state up to local transformation. This cluster state is a well state. So if it's easy to generate entangled states with photons, then it's easy to have your initial resource for measurement-based quantum computation. So it's easy to do measurement-based quantum computation with photons if you can generate entanglement between multiple photons somehow. And the question is how to implement gates. You implement gates by applying measurement in a particular basis, feed forward and read up. I'll give you some examples of that. So now let's proceed a bit further. Any more questions up to this point? Now we would like to do quantum computation these days.
You know, one information transferring for investment.
Now you don't have you. So one bit teleportation I introduced in the beginning.
Yeah.
So that was meant to motivate how measurement-based quantum computing works. So if you look at this initial diagram that I made over here, this diagram. So you have one bit of information over here, right? So one bit of information is available here that is being fed through and read out, and it determines what kind of gate has been applied over here. Okay. So you can have multiple bits. So here in this circuit, you have multiple bits available to you. The same idea that I started off with one bit teleportation, which is like a trick, has now expanded into bigger space. And now with this circuit, you can apply this gate to the logical qubit. So one bit teleportation is hidden in this. The many one bit teleportations taking place inside this circuit. So even though this is measurement-based quantum computation, but it has a circuit description for this as well. Okay, so now let's look at how we implement gates. But especially multi-qubit gates, the question about control phase gate, control NOT gate, and so on. So I haven't shown you even one multiple qubit gate, but I am going to move in that direction. So right now I'm going to show you some results, and in the later half of this lecture today, I will show you how to do some calculations. So how did I get those results? I will show them in Mathematica. So seeing is believing. Right now you have to trust me that this is what we get. By the way, this original description that I've used so far in my lecture today was inspired by 2 or 3 articles written by Michael Nielsen. The original articles about measurement-based quantum computation. Now the examples that I will take are from Anwar work. It was published in Nature. It was the first experimental demonstration of one-way quantum computing. It's called one-way quantum computing because it's irreversible. It's based on measurement. You can't reverse the process. So, and it's a great example of breaking the myth that measurement is bad for quantum computing. Measurement can be good. It's not that evil. It can also be made to serve a purpose. Now, some examples I would like to give is, and now I kind of take you from Anton Zalina's work. Okay, this is a cluster state. It's 4 physical qubits and 1 logical qubit. Now, this cluster state, if I were to do computing with this, with the mechanism that I mentioned, that is, you first of all prepare this state. So this is 4 qubit state. You can prepare this by shining a UV pump beam on this tool and passing that pump beam to it twice. I'll show you how electrons are generated. So you prepare this cluster state. Okay, it's a highly entangled 4 qubit cluster state. You prepare it, and then you do a measurement basis alpha basis. Your outcome is 0, you proceed forward. You do a measurement on the beta basis. Then you do a measurement in the gamma basis. And you final readout is here. You have implemented a 1 qubit rotation. Full 1 qubit rotation. Okay. So if alpha, beta, and gamma are the measurement basis for these 3 qubits, and time is progressing in this manner, then what you've really done is you have, let me also label 1 to 3, 4. What you've really done is you have applied this sequence of operation H, G minus alpha, H, G minus beta, H, G minus gamma to your side. So cluster computing on this cluster state in the basis measurement with alpha, beta, and gamma implements this arbitrary single qubit gate. So you don't need to apply the gate, you just do measurements one after the other. Okay? And I'll show you that this is when I show my calculations. Okay? Now, if I have a state of this cluster state of this kind, that follows a linear cluster state. This is, let's call it a box cluster state. This can also be generated in the laboratory with 4 physical qubits. Now I have 2 logical qubits. So now I have the potential of applying a 2 qubit gate. Now if I were to do a measurement on the basis alpha and beta, measure in alpha basis here and measure in the beta basis here, I've actually implemented a 2 qubit gate. And I'll prove that after the break. So what the circuit that this corresponds to is the following. This is my first encoded qubit, the second encoded qubit H, G minus alpha, H, G minus beta. So it's phase gate here as well. This is the circuit that I implement. Now this is the 2 qubit gate. A genuine 2 qubit gate. By controlling the values of alpha and beta, I can make this into a phase gate. I can make this into a control NOT gate. I can make this into any 2 qubit gate that I desire. Okay, I just have to control my measurement basis. I just have to find out and figure out my measurement basis. So at first do a measurement on qubits 1 and 4 as I mentioned. In some basis alpha and beta, and then a readout over here. This is tantamount to. Tantamount means it leads to it. It is equal to applying this quantum circuit, which is a two-qubit gate. This is how I implement a control phase gate. If my alpha and beta are chosen such that I think one is 0 and another is pi, I will have implemented a phase gate, control phase gate into two qubits. So I just do measurement on particular basis, I will implement a phase gate. I'll show you an example for this. Okay. Now, this is a box. A box cluster state. This is another example. Like horseshoe cluster state. This implements this state, two-qubit gate. I'll show you an example. Another. So by the way, in the logical space, in encoded space, you have two qubits, but in physically you have four qubits, or two logical qubits. Okay. So this implements this gate. Two-qubit, a genuine two-qubit gate. Okay, so these two are examples of horseshoe gates, and actually they will also starting off with an entanglement state. Your entanglement will actually increase after you pass it through this circuit for different values of alpha and beta. So this is how the entanglement can probably increase in cluster state. So this is the general scheme of cluster state quantum computing. We can implement one qubit gates and we can implement two qubit gates by the proper choice of creation of the cluster state and the proper choice of the measurement basis. So these are four examples, and I'll probably take one or two of these examples in my calculation, and I will show you. But one thing I would like you to remember is that I will also write on the blackboard because I will need to use this later on. That these four kinds of states, these three kinds of states, we correspond to physical qubits, of course, four physical qubits, and each one of them has this physical state cat representation, like the cat representations that we found for the two qubit cluster state and the three qubit cluster state. They also have cat representations, and that cat representation is 0 plus plus just writing this down because I can use this later. So this is for cluster 4 qubit. And the box 1, 2, 3, 4. The box cluster state. So this state differs from this state in these signs, this sign and this sign. Rest are the same. So these are the physical qubits that are required to simulate that cluster state. Now, these physical qubits have to be prepared inside the laboratory. Right? So you need 4 photons that have this quantum state. I will show you how Anwar's experiment generates this quantum state, which is equal to this quantum state up to a local transformation. Okay, and how this state can be achieved from this state. So how down conversion can create these cluster states, and then you simply have to do measurement and find a readout. And you have done a 2-qubit gate, or phase gate, any unitary operation on 2 qubits that would likely use for Deutsch and so on. I'll also give you an example of a full implementation of global search algorithms. Probably today or tomorrow, but I'm going slow here so that everything is clear. So is it good time to take a break?
Yeah. Let's take 15-minute break. Yeah. Can we have a group photo or you want to see? Yeah, let's come to the stage.
So turn on the lights. All right, so let's try. Can you stop the audio? Also, here. Can you tell me some? There's some echo. Even though not sure why. Can you stop the sound from here? This is not connected.
Bunun mikrofonu açık olabilir mi? Bir yerden alıp bir yere veriyor da onu anlamaya çalışıyorum.
Hello. I think. Hello. I think it's saying
Yok, kapalı diyorsun.
It just took me some longer to set this thing up. So now we will kind of show you some calculations. First of all, let's define the Pauli operators. So I define Pauli operators in this software. Okay, so my X Pauli operator, I call it AX. This is 0, 1, 1, 0. Okay. Likewise, I have my Y operator. 0, minus iota 0, and my Z operator is a diagonal matrix 1, 0, 0, 2. I define Hadamard gate H 1 square root 2. This one, I think you get a big idea. And then define X gate to some angle theta. So this is matrix exponent minus iota into theta into AX by 2. Okay, so this is my definition of an X gate. Oh, sorry. Okay, and likewise I want to identify the Y gate and the Z gate. The good thing about cluster state computing is we only use single cube, there is single qubit measurements, and you just measure a single qubit at one time. Z gate as well. And then you can prove the different identities. For example, H into A, Z, and A X into H, they are equal. Okay, so HX, HZ is equal to XH, right? So, is this true? Yes, it's true. So, all of these identities can be proven by explicit calculation. If I have an X operation about an angle beta, followed by a Z operation, AZ, and if I AZ, X minus beta, they would be the same. Okay. So all of the identities that I mentioned can be proven by explicit calculation. So now what I would like to do is I would like to start off by the 1 qubit gate, and then I'll give you an example for 2 qubit gate and how this cluster state process works. So I will first of all draw this state here. One linear 4 physical qubits. I want like to draw this state. So I've already mentioned to you the physical form of this state. It corresponds to a physical gate, a physical ket representation, and I could also try to come up with what that representation is. For example, let me define a plus state. A plus state is 1, 1, right? I'm ignoring the normalization constant. This is my ket plus state. Now I need to find a tensor product. So I define the tensor product between two entities, A and B, as the canonical product of A and B. So I define tensor product as well. This is how I define a tensor product, a function that computes the tensor product. Now I have 4 qubits. So first of all, I prepare those 4 qubits, each one of them in the plus state. So I do tensor product plus with a tensor product plus with a tensor product of plus and plus. Okay. This is what I get. I get an equal superposition of all the states. So what I've done over here is I've computed this thing. So I'm preparing the cluster state. Now I need control phase operation between 1 and 2, 2 and 3, and 3 and 4. Right? So I need to define control phase between 1 and 2, control phase between 2 and 3, control phase between 3 and 4. So a control phase between 1 and 2 will be control phase, say U phi, the control phase between 1 and 2. This is between 1 and 2. Nothing happens to the third qubit. Nothing happens to the fourth qubit. A control phase between 2 and 3 can be represented as U phi identity 4, and so on, right? So this is how I define control phases between 2 qubits in a 4 qubit set. I can do that easily. So first of all, I define my U phi CP, that's called CP. So this is when I want to do analytical calculations, I prefer this software, this Mathematica, which makes it easy for me to understand what's going on. So I define the control phase gate between 2 qubits. This is the diagonal matrix 1, 1, minus 1. right? So it's this matrix. So CP between 1 and 2 is tensor product CP with a tensor product. Okay, I also need to define the identity matrix. So identity matrix of size 4. Let's call it, let's give it a name, I. Let's call it I. Okay, so this is my identity matrix. So CP, CP, I. This is the first thing that I've written over there. And it's, of course, it's a 4 qubits, the 16 by 16 also identity matrix of size 2. So this should be a 16 by 16 size matrix. Okay. So this is control phase between 1 and 2. Let's write a control phase between 2 and 3. CP 2, 3. This is I. CP. And let's write between 3 and 4 as well. 4. I. Okay. Now I take my this state, which I have created, tensor product of all the plus states, and successively apply all the control phase states. Okay. So this is my this is the physical description of cluster state, what I have over here. It's just a column vector with 4 qubits. This is the coefficient of 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, and so on. So a column vector, big column vector. Okay. Now I would like to kind of show that this is equal to, with all the C phase operations, C phase 1, 2, C phase 2, 3, C phase 3, 4, this is equal to 0 plus 0 plus 0 minus 1 minus plus 1 minus 0 plus 1 plus 1. This is equal to this. Now, why do I need this? Because when I generate entangled photons, I will show that entanglement is equivalent to this. This is an entangled state. So let's see if this is my linear state, linear, let's call it linear 4. And let's see if that description that I've written over there is also correct. So I take the tensor product. So I define 0 quantum state as 1, 0. And I define ket 1 as 0, 1. Now let's find out tensor product of 0. In fact, I've already written this in another file. Let me see. Let's copy from there. Tensor product of 0 plus 0 plus 0 minus 0 minus 0 minus 1 minus 1 minus 0 plus 1 plus 1 minus. So I also need to define a minus state. So let's see. Is this equal to linear 4? Okay. So now what I've shown is that this state, this cluster state, which was formed physically, mentally, mathematically by taking the plus states for all the 4 qubits and then applying control phase operations between any 2 physical qubits between which a bond exists. I get this state. This is my description of the starting cluster state corresponding to this diagram. Now what I would like to do, I would like to measure in alpha basis here. When my outcome is 0, I move on, measure in the beta basis here. When I measure in the alpha basis, this qubit goes away. Then I'm left with a 3 qubit state. So my dimensionality of the system is decreasing successively. Then I measure this qubit along beta. When my outcome is 0, I proceed. Then I measure this qubit along gamma, and then I proceed. So I have a multi-stage computation. That computation only involves measurements followed by feed forward. You measure and then you go ahead. Measure, you ignore that qubit then. I mean, that qubit has been demolished, and then you move ahead. So let's now kind of measure the first qubit in the state along the axis alpha. So if I were to do that, so how? So how do I do it? So I know that measure the first qubit means I do this. R Z. Let's do RZ minus alpha. So I measure along alpha. So to the state I apply an operation through minus alpha. So I measure along alpha. To the state I apply an operation along Z axis through minus alpha followed by alpha. So this is what I'm doing to the first qubit. This is my first qubit. And then I measure it. And when my outcome is 0, I proceed. Okay, let's try to do this on the first qubit. So I need to apply a Z gate through minus alpha on the first qubit and a Hadamard gate on the first qubit. H Z minus alpha. But now these are just single qubit gates. But I have a single qubit gate divided into 4 qubits, so I need to find a tensor product of this with identities for the other 3 qubits. So this is just basis rotation on the first qubit. And this applies to my input state linear 4. Okay, I simplify this a little bit. Okay. So I don't really worry about the normalization under root factors, but this is the state that I get. Now in this state, this is now a 4 qubit state. But I would like to find out the outcomes where my first qubit has ended up in state 0. So if I put this in a column vector, these are 16 elements. So the first 8 of these elements will correspond to when I have projected the first qubit to get 0. So this is how I've ordered this. This is 0, 0, 0, 0, 0, 0, 0, 1. First 8 qubits have, first 8 of these coefficients have a 0 in the first place. So I just take the first 8 of these terms and proceed forward. Okay? So this really means that I have 0. So this is my first qubit. My other 3 qubits could be anything. These are my qubits 2, 3, 4. I take all of those coefficients for which the first qubit is 0. And in this column vector, I have 16 elements. The first 8 of these will have 0 in the first position, and the other 8 will have 1 in the first position. So I just take those outcomes for which the first 8 terms, I will only take those terms, and those will form the projected state for these 3 qubits. Okay? So this is like a kind of cross operator if you more technically savvy. So what this does is, in other words, this is like projecting on applying this projector onto your 4 qubit state. You're left with a 3 qubit state. And if I take the first 8 of these terms, so I take the first 8 of, so if I call this some intermediate, you take, sorry, this is the first one. Okay, so I just take the first 8 terms. Could be more efficient ways of doing this. 1, 2, 3, 4, 5, 6. This is my stage 1, after stage 1. So these are the first, after stage 1, this is the state that I generated. Now it is a 3 qubit state. Now I measure on the second qubit. The first qubit has just disappeared. I make a measurement on the second qubit along beta. Right? So how do I do that? I take my stage 1. Take my stage 1 and measure on the first qubit, go to the second qubit. The first qubit has just gone away, and I do nothing to the other 2 qubits. Okay, so now a smaller dimensional system. I measure along beta. Okay, so I do a AHZ alpha minus Z minus beta operation on stage 1. This is what I get. Okay, now I have to identify from when the outcome is 0 at the second stage. These will be the first 4 terms again. So let's call this Q2. Take first 4 terms. So Q2 1 on Q2 2 on 3 on Q2 4. This is the outcome after stage 2. Now I do measurement along gamma on the third qubit. First 2 qubits have gone away. I have now 4-dimensional system with 2 qubits left. So now let's do a paste. On stage 2, I do 8 minus I just have 2 qubits left. TP, H, G, gamma, gamma. I do nothing to the last qubit. Alright, so this is now the first 2 qubits. If my measurement outcome is 0, my measurement outcome is 0, and then look at the 4th qubit. So the first qubit is 0, 0. This corresponds to 0, 1. This corresponds to the 3rd qubit is 1, so I ignore these. This is when the outcome is 0. When the outcome is 0, these 2 terms will represent what state will be the 4th qubit in. Last qubit in. So now we have the readout stage. We've measured this in alpha, measured this in beta, measured this in gamma, and now when we've made a measurement, the first qubit has been projected into some state. That state is given by these terms that I've shown in blue. So now if I just kind of extract this whole C and I call this the output to the readout. I can try to let's try to simplify this if possible. Well, these terms I think can be simplified. So this is this thing, and this thing is really so this is the output, and what I have over here is some of these terms is something very simple, and I ignored the normalizations, because I lost track of the normalization factor. So this is the output that is received on the first qubit. Only by preparing a cluster state and measuring in successively, one after the other, doing projective measurements in particular along particular axes alpha and beta and gamma. The final qubit, physical qubit, is left in some state. Now, I would like to show that this is what would happen if I were to apply an arbitrary rotation operator. This is exactly equivalent, should be equivalent to the following. This operation, this output has achieved a single qubit gate, an arbitrary single qubit gate on one logical qubit. 4 physical qubits, 1 logical qubit. So now what I would like to show that is this operation the same as when I input with get, when I input with this encoded state, and I just have a single encoded qubit, just one logical qubit implemented to 4 physical qubits. And a gate implemented on 4 physical qubits, but it's equivalent to an arbitrary rotation acting on a single qubit. Let's see if this is true. So now I shift gear and look at this single qubit operation and see the two outcomes are equal. Unless I've made some typographical error, they should be equal. So let me try to simplify this over here. Complex expand. Okay, then anyway, so let's try to give this a color. Sorry. Okay, so that I know what's going on. So now, suppose I have physical state P, a logical state P, and on this I act Z minus alpha followed by H. Then I have Z minus beta followed by H. Then I have Z minus gamma followed by H. Let's try to simplify this. Let's try to kind of like this. Okay, let's try to do this one. Are they the same? I think they are the same. So if you look at the top, this has been achieved by preparing the cluster state, measurement on one qubit, wash it away, keep it, just use the outcome, and look at this subspace when the outcome is 0. Then do a measurement on the second qubit in a particular axis. Look at the subsequent qubits when the outcome is 0. The third qubit, measure along an axis, and just look at the final qubit at the readout stage. Only measurements and one-way progression. You just have to prepare the initial cluster state, one-way progression, and you get an output. This is the same as having a logical qubit, one qubit, and an arbitrary rotation. So this quantum circuit is implemented by a measurement-based quantum computing scheme. Totally identical. Now you can choose alpha, beta, and gamma to your desire and have any arbitrary single qubit rotation purely by measurement on a photon. Purely measure the polarization of a photon with beam splitters and get an arbitrary rotation. It's only that the only difficult task is preparing the cluster state, and that photons will be naturally inclined to do so, as I will show you in a while. Now let's look at a 2-qubit gate. Exactly the same process. And the gate that I would like to now show is any questions about this? I hope I'm really clear, and I've shown the working step by step. Let's try now to do this cluster tree. Let's say let's look 1, 2, 3, 4. Now remember that as far as the cluster state preparation goes, this is identical to this. If I label the qubits in this fashion, control field between 1 and 2, 1 and 2, 2 and 3, 2 and 3. It's just that I've drawn this cluster in a fashion that highlights which order do I use for measurements. So I first do a measurement on qubit 2 and 3. It doesn't matter whether I do it on 2 before 3 or 3 before 2, doesn't matter. I can do them successively as well, at the same time as well, simultaneously as well. So I do a measurement on these 2 qubits. Now I have 2 logical qubits instead of 1 because I just twisted the cluster a little. Now I do a measurement about alpha on the second qubit, measurement about beta on this qubit, and 1 and 4 are the readout qubits. This implements a 2 qubit gate. It can be controlled phase gate, controlled G gate, and controlled NOT gate, depending upon alpha beta again. Alpha and beta, sorry, yes, there's no gamma here. So now let's see how this pans out. So my initial cluster state is still linear 4, is still the same state physically. However, now let's call it a horseshoe. Okay. Now, what I want to do, I want to do a measurement on qubit 2 and 3. So, and do a measurement horseshoe. I apply an alpha rotation over qubit 2. So if I were to do that, I get H, Z minus alpha. This is on qubit 2, second qubit. So I need to find the tensor product of first we have an identity, then I have this thing, then I have identities on the last 2 qubits. So this is over here. This is qubit number 2. I apply measurement transformation, basis transformation on qubit number 2. This is nothing happens to the first qubit, third qubit, fourth qubit, something happens to the first qubit. So I apply this onto the horseshoe state. I'm measuring the second qubit. So when I do this, let me simplify this. Okay, at the same time, I want to do a measurement on the third qubit as well. And measurement on the second qubit actually commutes with the measurement on the third qubit. So I can now do measurement on third qubit in the same go. So I follow this by what's going on? whatever you can TP. Oh. No, this one. This works. Okay. Now I can TPI proteins TP TP. It will on the third qubit number 3. Okay, I simplify this. Try to simplify further. For this something, alright, so this is my state.
We should set control at same time, of course, when you measure the second one, then you left with the three trees. Should you do based on the three trees or?
So I can measure them at the same time, I can measure them one after the other.
But then if you measure one after the other, then you operate on the three trees one after, right? I mean,
Yes, but it doesn't matter because these commute. This operation commutes to this operation. And now I'm looking at when both of these outputs are 0. It doesn't matter. You can do it at the same time or different time because they are on different qubits. These operations commute. Z alpha on the second qubit commutes with Z beta on the third qubit. They commute, so you can do them in succession together, doesn't matter. So now this is my state. It has 14 elements. Now I want to look at the elements when this outcome is 0 and when this outcome is 0. So if I kind of label my states, first qubit 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0. Now see when the second and third qubit both are 0. So this case, this case, this case, and this case. So I take the first, second, 9th and 10th terms out of this. That's when both of these outcomes from those measurements is 0. So I just take these 4 terms. That will be the state of these qubits. So in this scheme, I take the first, second, 9th, and 10th term. That will give me the quantum state of qubit number 1 and qubit number 4. If I'm not making any error, this should work. So take part Q3, the first term, part Q3, second term, part Q3, the third term, Q3, fourth term. Oh, sorry, 9 and 10, 9 and 10. So this is after the first stage, so this is stage 1. So I have these 4 terms here. So these 4 terms represent the state of qubits 1 and 4. Okay, now what I would like to argue is that we have 4 physical qubits. Doing this operation in this measurement-based fashion, in this cluster computing fashion, is equivalent to having this circuit. Which is a 2-qubit gate on these logical qubits. First encoded, second encoded. So this kind of measurement gives the same, it implements a 2-qubit gate. This could be controlled phase, controlled not, depends upon alpha and beta, the choice of alpha and beta. Okay, so let's see if what happens to 2 qubits when it sees this kind of quantum circuit, and whether the measurement based outcome matches or not. So let's call this the output from MD2C. So just 2 measurements in the first stage, alpha and beta, automatically transforms the 2 physical qubits. So let's see if now implement the quantum circuit. So I start off with a tensor product of 2 plus states, and on these plus states, I apply the control phase gate CP. Let me just color this. Okay, I first apply control phase gate, then I need to apply Z minus alpha H for tensor product. This is on the first qubit with identity. Where does this gamma come from? Okay, I'm using, let's use beta here. Let's use beta here. Instead of gamma, let's use beta. So now I have beta here. Excellent. Okay, so if I just so now what we've done through a measurement-based scheme, preparing a cluster state in a particular fashion, through a measurement-based scheme, we have implemented a 2-qubit gate, a multi-qubit gate. And likewise, we can extend this to multiple qubits. We can have any unitary operation encoded through different schemes. So you can have cluster state of this kind, you can have a horseshoe which is in the opposite direction, you can have a box state, and so on. So if for example, so the two are equivalent. Measurement-based quantum computing can be simulated through quantum circuits. If you know quantum circuits really well, you can see that measurement-based quantum computation with cluster states also works. Now, if I take my output MBQC, here is my output state. Let's see what do I get when I have alpha equals say 0 and beta equals 0. Say, suppose I get this state, control phase. This is how we implement the control phase gate on 2 qubits. This is how you could do it with photons. Just prepare the cluster state and do measurement. it implements a 2-qubit gate. If I were to put this 5, this is also another control phase gate. If I put this 5/2, this is a state that you get. This is the higher margin control phase gates. If I put this 5/4, I can generate any state, any quantum, any 2-qubit gate I like. So the 4 cluster states that I have presented, they are universal. They can give universal quantum computation. The linear cluster state can give any 1-qubit gate, and the horseshoe can give any 2-qubit gate. Just from measurements, which are simple to do with photons. Now, if you look at the original paper from Zeilinger, I have extracted this 2 slides that I wanted to show you here. How do they generate this cluster state? So this is how they generate this cluster state. 4 qubit cluster, and I will write down the form for this in terms of polarizations. So what they do is, there's a BBO crystal here, and they shine a UV pump beam onto this ultraviolet light, and it down conversion takes place, and the pump beam actually, so in one stage of down conversion, these 2 down converted photons are created. Okay. Now this is a perfectly reflecting mirror. The beam bounces back and hits the BBO crystal a second time. And the second time, these 2 down converted photons are created. Now all of this happens very quickly. So you have 4 photons that are created in the states A, B, C, D. These are spatial more important of the photons. Now what happens is you have these compensators and these half-wave plates. Because when photons go through this crystal, there are walk-off effects. Walk-off effects means there are additional phases that are incurred by the photons that are unwanted. They have to be compensated by, this is actually a quarter wave plate. The compensator is a quarter wave plate. It compensates the walk-off effects. The combination of this quarter wave plate and this half wave plate then generates photons in a particular state that I'm going to show, and when this fall onto these beam splitters, polarizing beam splitters, they're in a particular polarization state. This is type 2 down conversion, spontaneous parametric down conversion. In the final form, the 4 photons, 1, 2, 3, and 4 are your 4 physical qubits. And they're in a particular quantum state in terms of polarization. They can be measured. And that quantum state is given as follows. The 4 photons are in this state. H, B, plus B, H. Let me just confirm this. Plus H, minus B. This is the state of the 4 photons. This is highly entangled. This is probably your first, maybe it was my first example of creation of a 4 qubit
photon entangled state. It's highly entangled. How do you check its entanglement? One way to check its entanglement, as I mentioned in the previous lecture, was to do a reduced density matrix. If I were to do a reduced density matrix of this 4-qubit state for 3 qubits, so I just trace out the first qubit. If I were to trace out the first qubit using the techniques that I mentioned in the previous lecture, I will be left off with another entangled state, which is the GHZ state. So if one photon is kind of removed from the system, the 3-qubit state also remains entangled. So this state is also robust against photon loss. The entanglement survives even if one qubit is measured from the system, it still remains entangled. If you have a GHZ state, and do this as a homework, if you have a GHZ state and you remove one photon from the system, which means you take a partial trace over one photon, the remaining state will become separable. But for this 4-qubit entangled state, you trace out one qubit, the remaining 3-qubit state also has entanglement. And you can use an entanglement witness. You can kind of have this operator say 1 over identity 3 times plus five plus there's an entanglement witness operator that can be defined. And this I think is 1/8. So if I take this entanglement witness operator, find the reduced density matrix. Suppose that reduced density matrix is rho. Take multiply this with the entanglement witness operator and find the trace of this. If I get a number which is smaller than 0, then the 3-qubit state will be entangled. So I can do tests for entanglement. These tests are not as simple as the positivity or the partial transpose test, but still you can define an entanglement witness operator and do a test. So now this state that is generated by this spontaneous parametric down conversion, this can be shown to be equivalent to a cluster state. This is a cluster state. How can we show that? We can show that by explicit calculation. So if I were to take this state. By the way, this is also very interesting. So if I have this ket and I form the density matrix for this ket, then the density matrix of this ket has all of these terms. This is the theoretical density matrix. So I just take this ket and form the bra, and I get a 16 by 16 size density matrix. Okay, this is the theoretical density matrix for this state, 4-qubit state. When you do tomography on this 4-qubit state, how do they do tomography? Simply by how I showed you how tomography can be done. You take the 4 qubits, and with each qubit you put a quarter wave plate, possibly a half wave plate or a polarizer, and you measure the outcome. Measure the number of photons coming here. So you do tomography with these outcomes, this outcome, the 4 outcomes. And then you can write all the equations and do a maximum likelihood estimation to find out what the density matrix is. So when quantum state tomography is done on this 4-qubit state, this is the experimental result. This is the real part. There should be no imaginary part. This is theoretical, and this is the experimental part. Okay, so to a very high fidelity, is this 4-qubit state, highly tangled state generator, which qualifies as a cluster state. Why does it qualify as a cluster state? Because if I were to take this state that has been generated, physically generated inside the laboratory, this is equivalent to a cluster state up to local transformation. So if I take this state and I were to do this operation, Hadamard on the first qubit, nothing on the second qubit, nothing on the third qubit, and a Hadamard gate on the fourth qubit, I will get this quantum state, the cluster state. So this state is the same as the cluster state up to local transformations. And you can implement Hadamard gates easily if you wish to do so.
So two beams.
Exactly. Exactly. So I can prove this as well. I think I'll attempt to prove this, but let me see if I am able to do this. First of all, I would have to, so this is 00111100. So this is 00111100. This is 0000. This is 11. This is 6. First term, 16th term, third. This is 4. So this is 3. So this is the fourth term, I think. And this is this is 12. 13. Let me see. 00000000. Youngsters, can you please help me here? 010. So this is this term. This is 110. 0011. And so पहली दूसरी तीसरी चौथी 5 6 7 8 9 10 11 13 16. So I have this row vector. Let's see. So I have this state, let's call it NT. So पहला चौथा चौथा चौथे के बाद आखिरी because everywhere so let's see what happens if I did an Hadamard on the first qubit. Nothing on the second qubit. Nothing on the third qubit, and Hadamard on the first qubit. Just ignore the normalizations for a minute. Okay, same.
The element be or just one.
Mhm. And oh, this one, this. Thank you. Thank you. So this is the cluster state. Okay. This is the cluster state, the horseshoe state, the linear state, the other horseshoe state. The box state can also be created by applying Hadamard on every state. Hadamard. That will create the box cluster state. So now your universal quantum computation with photons, with measurement-based quantum computing. So I think I've shown you how single qubit gates can be implemented, two qubit gates can be implemented, and an entire sequence of operations can be done just using a measurement scheme. So I've shown you theoretically in a logical fashion. I've also shown you through explicit calculations. And in fact, if I were to take the horseshoe state and do the measurement-based quantum computation, I can predict what the final density matrix is going to look like. It will have all of these terms. Try to do this as an exercise. And then, when the experiment was done, this is what the tomography revealed. If I were to start with the box state does not generate any entanglement. The box state density matrix looks like this is what has been generated. So now I think I've convinced you that with measurement-based schemes and photons, you can kind of recreate universal quantum computation, 1 qubits, 2 qubits. Tomorrow, what I plan to do now is to give you a quick review of the Grover algorithm and how measurement-based schemes can implement a useful quantum algorithm. I'll talk a little bit about quantum error correction. Finally, I would like to spend 1 hour on an alternative way of doing quantum information processing with spins inside of the field. So this is something that I'm very comfortable with, and it will give you a comparison of how photonic implementations take place and how other spin-based implementations unfolded. And then we can have some time for question answers and general discussion perhaps about the future. And does that look good for you?
Yeah.
Thank you very much.
Can you kindly save this PDF and email it to from yesterday as well? And whether you want a PDF or this mathematical file?
That's what we use.